In this lecture, we will discuss the power dissipation in one-dimensional transport by taking quantum point contact as a candidate system, and we also will look into the technological applications of quantum point contacts and atomic point contacts. The quantum point contact operates in the quantum ballistic regime. The assumption there is there are no scattering events when the electrons are traversing or propagating through the channel. But from the derivation for conductivity, what we are finding is the conductance of the channel is finite and it is varying in a step-like manner where E square by h is the quantum limit of conduction. But now the natural question is, if there are no scattering events in the device, then where is the power dissipated? Or where is this conductance, or where is this finite conductance or the finite resistance is arising from? Okay, where from we are getting this finite conductance and where the power is dissipated. So just to enlighten this picture, let's consider a system where the ballistic transport is happening. Mu L and mu R are the electrochemical potential on the source and the drain side, and I have represented the device as a black box in the middle. Okay. And as we discussed, there are no scattering events or there is no dissipation of energy in the channel. So now let's consider that an electron with energy E is traveling through the channel from the source side to the drain side or from left to right. The energy E is between the electrochemical potentials on the right side and the left side. That is the assumption. Okay. So the energy left behind at the source lead or source side by the hole which is left behind with the electron. When the electron moves from the source side to left side, is going to leave a vacancy there, it's a hole. And the energy left behind is mu L minus E, because hole, the lowest energy for the hole is actually the top or mu L level. Lowest energy for electron is the opposite direction, it's the bottom of the band. For the hole, it's the top of the band. They are just opposite. What generally is called the pebble analogy, where hole is considered as a bubble, or is analogous to a bubble in the water, where bubble has the lowest energy when it is on the surface of the water, or pebble, a stone, which has the lowest energy when it is in the bottom of the tank or bottom of the water. So generally, what we call say bubble pebble analogy. Okay. So for the hole, the energy left behind is mu L minus E on the source side. Now, the electron which crosses over the channel and reaches the drain side, because there is no energy deposited inside the channel because there are no scattering events. So there is no chance for that electron to deposit any energy inside the channel or in the channel or in the device, okay, or in the constriction. So the energy deposited at the right electrode, that is the drain, is E minus mu R, where mu R is the bottom, or the bottommost level which is available for the electron. Until mu r it is filled. Okay, so there are some levels at mu r where the electron can occupy. So the energy left behind on the source side is mu L minus C, and the energy deposited on the drain side is E minus mu R. So the hole and electron, in the process of moving from the energy level E to mu L on the source side and mu R to E to mu R on the drain side, they will dissipate the energy on the source and drain, because there are a lot of states there that I can actually undergo scattering. Inside the channel, there are no states. Okay, because there are no states where they can actually scatter to. So total energy dissipated in this process is mu L minus E plus mu R minus E. This is the source side and this is the drain side. So that is the E into VSD, where VSD is the applied voltage which actually brings the mu L and mu R at different levels. Okay, so the E VSD is the applied voltage. Okay, E VSD. So what we are seeing is the energy dissipated by the electron when it is in a level on the source side between mu L and mu R, okay, is independent of E, because that is just EVSD, the applied voltage. It doesn't depend on which level electron has started and which level the electron has ended. It actually just depends upon what is the potential difference between the source and drain side, or what is mu L minus mu R. It is an interesting point. Okay. Now, the power dissipation. So we know where the energy is deposited. Okay, source side and drain side, and there is no energy deposited on the drain side. And we need to know what is this power and how is that related to the resistance that we are measuring. Okay, so let's consider that we have applied a voltage VSD, and the time tau is what the electron takes to start from the source and end the drain under this voltage. Okay, so the power dissipated for the electron between the source and drain is dP, is this voltage divided by the time taken, this tau. Okay, EVSD by tau. Now, let's look at what is the current. Okay, we want to calculate the power, so we have the voltage now, and we need to know the current. Then we can calculate the power from that. Okay, so the current due to this electron in this small voltage range, the assumption here is EVSD is always small. It is much smaller or within the spread of the Fermi distribution. Okay, width of the Fermi distribution. So the current is the conductance into voltage, that is 2 into E square by H into N. This is the conductance. Okay, the conductance, this is G, the conductance. So into N. Okay, E square by H into, this is conductance quantum into the number of channels. Okay, so the current is 2 E square by H into N into dV. Now, assume that this voltage dV is correspond to an energy window dE. So that is E into dV is dE, the energy window. Okay, so we can rewrite the dI as 2E by H into dE, where E into dV is dE. Okay, so 2E by H N into dE, that is the current. So now current is also of the form charge transfer rate, or charge divided by the time taken for the charge to move the system, that is tau. So di is E by tau. Okay. So what we can get from here is, when you equate these two, we can get 2n by h into dE correspond to tau. From here, what you can get is 1 by tau is 2n dE by h. Oh, that is the transfer rate. So the power dissipated from this expression, same here, is EVSD divided tau, but tau is 2n dE by h. So what you're getting is power dissipated is of the form 2n EVSD dE by h. Okay. That is for one electron, or that is for the state which is between mu r and mu l. But now remember, there are a lot of states between mu l and mu r, or mu r and mu l. So the integral between mu r and mu l over energy within this range mu r to mu l is going to give you the total power. Okay. So the total power is the integral of this dp in the energy range mu r and mu l. Okay. That is the total power dissipated. Now, this is the same formula that we just saw in the previous slide. And here we need to consider mu r and mu l, because our assumption is there are no other states taking part in the transport. Okay, and all this discussion happens in the linear transport regime, where most of the transport is between mu r and mu l, and the Fermi distribution is mostly sharp. Okay. So when you integrate it, what you are going to get is 2n EVS d by h, mu l minus mu r. Okay. And that's going to give you 2n EVS d by h to be ESD, because mu l minus mu r is VSD. Okay. So this you can write as V square SD divided by h by 2e square n. Okay, the power. So what that means is, this is of the form P into V square by R. P into V square by R. This was form. Power is V square divided by resistance, where this resistance is h by 2e square into n from here. What that means is, the resistance that you have attributed to the one-dimensional transport, that is h by 2e square divided by n, where n is the number of channels, is actually the resistance corresponding to dissipation at the source and drain region. There is no dissipation in the channel, so this resistance cannot be from the channel. Okay, that if you consider this problem conceptually, there are states, propagating states through the channel, but none of these states are backscattered in the channel. The propagation through channel is streamlined, and these states are orthogonal, so there are no scattering between the states either. Okay, so there is only one way that you can get a resistance, that is when this channel meets the bulk or meet the source and drain. So whatever the quantized resistance that you are measuring, that is actually the contact resistance of the lead. Okay, but it is kind of anticlimactic or surprising, because we have worked all this quantum transport formalism and to understand the condensed conduction and all the condensed resistance to the channel. But what you're now seeing eventually from the power dissipation is this is nothing but a contact resistance. But now you have to be a little bit careful here. When I say contact resistance, it doesn't mean that these are the resistance where you get when between the wire that you're connecting to the device at the contact pad. That's not what it means. For example, if I have a device and these are the gates and there are condensed transport through the channel, and I have source and drain contacts, okay, where you are going to connect the current or voltage leads, okay. Now this resistance RC is not the resistance here. This is not RC, not the RC I'm talking about. RC I'm talking about here is you have integer number of channels, integer number of modes in the channel, and as soon as these modes leave the condensed region or area, this is going to merge with many number of modes here, because you have discrete number of modes in the center, only discrete number of modes, okay. Number of modes here is discrete. But here you have continuum of modes. You have so many infinite number of modes in the bulk on these two regions. They are still within the sample, within the two-dimensional electron system. This point is not a two-dimensional system here, because there we have deposit some metal, some processing, diffuse some dopants into the region. You have done some processing there, and that region doesn't qualify to be a two-dimensional system. Okay, so we are not discussing that. What we are discussing here is the place where these one-dimensional modes meet with the two-dimensional modes. Okay, that is immediately outside the constriction. This resistance RC, whatever we are discussing, is the contact resistance of those regions, the source and drain region. When I say these are the regions, okay, this is the source and this is the drain. So that is where the power is dissipated. Of course, you can have some other series resistance in this region, but that is not the discussion here. Okay, you can have an additional dissipation there also, but that is not a quantum transport feature. Okay, that is not where the condensed, whatever discussion what we have done is happening. Okay, so the contact resistance RC, which is condensed, which we have seen, which is basically the condensed resistance that we have derived for the channel, refers to the immediate region where the one-dimensional modes meets the two-dimensional system. Okay, that is the summary or nutshell of the discussion. Okay, now let's look at some interesting applications of this point contacts. When I say point contact, that includes quantum point contact, which we have discussed, and also includes atomic point contacts, which in really, you know, atomic level constrictions, okay, for atom-atom contacts. So what we understood is the conductance of the channel is quantized in 2e square VH. So if you look at the transconductance, that is the gate voltage versus the current through system or conductance. There are really nonlinear, very sharp drops in the current, where a small change in the gate voltage can give you a large change in the conduction. It's highly nonlinear device there, which is what you need essentially for any kind of sensing applications or detection of charges. Because here, a small change in the gate voltage means a really minute change in the electric field. Okay. So the point here is a small change in the electric field or a charge configuration in the vicinity can give you a change in the conduction. Here, this is a picture of one of the device where you have deposited surface gates. What you are seeing is a gate pattern on top of a two-dimensional electron system, and you are going to apply negative voltage. When you apply negative voltage to all these gates, what you are going to get is you get a trap for electrons here, and you get a channel here as represented. So this channel is a quantum point contact channel when the conditions are satisfied, such as the mobility, temperature, energy, scales, everything. But assume that all those things are met. Now, you have a trap for electron here. This actually can hold electron for certain duration and release it, and you can control it by controlling the voltages on various gates. That is the discussion for our next module. So I don't want to basically, break the surprise here. Okay. So, but for the time being, to understand the technology, assume that you have a trap for electrons. The holding time or the release time of the electrons in the trap you can control. But this is, and also one electron at a time. That means you can control the movement of one electron through that. One electron is a really, really tiny charge in the solid, okay, which has a lot of electrons floating around. So using the quantum point contact and biasing it to the nonlinear sharp regime in the transconductance curve, you can sense the electron jumping in or out of this trap. So what you're seeing here in this plot is the actual data where this represents the transconductance. That means the conductance of the QPC as a function of the electric field or gate voltage. So in this case, you can see that there is a small bump in the conduction in the middle here. That actually corresponds to an electron moving out of the dot when you see the voltage in the negative direction. So just to understand the process a little bit more clearly, when you see the voltage, this is Vm, whatever is labeled there, you are going to push this electron out because you are creating a negative field, okay, of electric field which pushes the electron, or you are basically increasing the energy of the electron, energy of the electron states inside the trap, inside dot. That is what is represented here. So you will push this levels up. So whichever the electron which was here, that will jump out. Okay. Of course, then another electron will jump in once it jumps out. This is like a turnstile device where only one electron can go through system at a time. Okay. So what that means is, if you sweep this level up, one electron will jump out, or the charge state of the dot will change. If the electron had n electron, then it will have n minus 1 electron. If it had n plus electron, n plus 1 electron, then you will have n electron. So in this side, you have n plus 1 electron. In this side, you have n electron. So when you sweep this, at some point of time, the electron will jump out, and that is going to get captured that event will be captured by the QPC. And the small change in the current or the peak in the conductance is telling you that there is an electron tunneling event had happened. Okay, and this is technologically really important, because in this range, measuring the electron tunneling event by measuring the current through the dot is very almost very tough, or it's almost impossible, because the current levels are in auto amps or even lower. So you cannot measure anything with any this current with any of the commercially or even homemade preamplifiers. So you cannot measure the current through the dot in this regime. You have to resort to sensing the electrons or sensing the motion of electron and then converting that to current. Okay, so these devices are really sensitive. We can actually sense like few micro electron per root hertz. Okay, that means a fraction of an electronic charge. Okay, and you can detect one electron, most of one electron at a time, which is highly beneficial for various technology and highly sought after for technology such as charge counting applications, metrology, and also reading out the state of a quantum dot based qubit. These devices are gated devices, so it is very easy to integrate these quantum point contacts to other gated device, because you just need to add one extra gate on the structure. Okay, just like what is shown here, you have this dot, you add these gates, you're going to get two quantum point contacts, one on this side and one on this side. You got two. Okay, so it's easy to integrate this quantum point contact with the other gated device, and it finds a lot of applications in charge counting and charge detection in metrology area or quantum computing technology. Okay. Now, you can also sense the charge in real time. Real time means you can detect the follow an electron where it is, or you can calculate the time spent by an electron in certain region. Let's go back to the same device what we discussed before in the previous slide. Here, we are detecting the current through this QPC, the channel on the side, in the time domain. Previously, we actually did it in the voltage as a function of the voltage. So when the voltage was in this range, the electron was inside the dot. When the voltage was in this range, the electron was outside the dot. But we didn't get any information on how fast the electron has gone out. Okay, temporal information or tunneling time, we don't know. So here we can measure the change in the current through the QPC as a function of time, and you can get what was the fraction of time the electron has stayed in, what fraction it has stayed out. Because when the electron is inside the dot, this is going to feel a higher or more negative voltage or lower voltage on the gate. That is how it's getting translated. Okay, the effect is getting translated. So you will measure a lower current level. When the electron is outside, it's a less negative field or lower energy, the current will go up. Okay, so all up, the duration of this up state correspond to how long the electron has stayed outside, or the down will tell you how long the electron has stayed inside. So you can directly get a timestamp or snapshot of where the electron at a particular duration by just taking the snapshot of the current through the QPC during that time. And here, each of these event represents one electron. So you are sensing the motion of one electron in real time through this circuit. And you can also do this in much faster scale. Here, this is done at 1 millisecond time scale. You can do in microsecond time scale by certain other technology called radio frequency quantum point contact, which we will discuss in detail when we do the metrology session later. So, in nutshell, you can have the same QPC but in slightly different microwave circuit. When you embed that, when you embed this whole device in a microwave circuit, you can operate this QPC at much faster time scale. The inherent speed of the QPC is in terahertz. So operating in gigahertz is not a problem for the device, but it is actually the technology, how you operate this device in the gigahertz or nanosecond time scale, and how to get the signal out of this QPC. That is a technology problem. It's not an inherent problem of the device. So what I'm saying is you can operate this device in even faster time scales than this. That is one research is going on currently. Now let's come back to the cousin of the QPC, that's atomic point contact. Okay. So atomic point contact is nothing but it's a contact between two atoms or two surface or two conductors. In this landmark experiment, what they have done is they had a microfabricated atomic point contact where you have a vibrating beam or a wire or a string, and there is a small knife edge kind of contact here, and this is the circuit diagram where the knife edge is represented here, and you can measure the conductance between these two and measure the distance between the beam and the knife edge. Okay, it's like a AFM or a STM experiment where you have a beam which actually can move or oscillate, and you have a knife edge which is coming here, and the conduction and the contact here is in the atomic scale. So the conductance through the circuit is a strong function of the point contact channel resistance. Sorry, strong function of the gap. So the resistance can give you an idea of the motion of the beam when biased in the sharp regime of the transconductance curve, and that's what they were doing. And again, they have utilized a similar technique what is discussed, what is shown here. We will not discuss the detail, that we will do in some other lecture later. So it's a very similar circuit here also, and what they were able to do is they can sense the motion in femtometer scale. So the sensitivity what they have extracted is in femtometer per watt hertz for this case. Okay, so these are the two examples from many where these point contacts are used for ultra fast and ultra sensitive metrology or detection applications of charge or any other parameter which is associated with the charge. Okay. Now, this is an example where you can probe a lot of fundamental physics by tunneling experiments conducted using QPCs. This is a landmark experiment where you are probing the statistics or the physics of quasi-particles of fractional quantum Hall states. So fractional quantum Hall quasi-particles can have abelian or non-abelian statistics, and this is an active area of research and still not completely settled. Okay, so the non-abelian systems, if you have a system with non-abelian particle, that has applications in error-free topological quantum computation. Okay, and it is predicted that some of the fractional quantum Hall states, such as 5/2 or 12/5 states, are non-abelian. But there are a lot of experiments going on to confirm these claims or confirm these proposals, and the field is not completely settled either. Okay. Now, just looking at the quantum Hall's system, the fractional quantum Hall system and quantum Hall systems are similar in terms of the edge states. I mean the concept of edge states So what you have in a bulk is you have localized electron states in the middle, which doesn't contribute to conduction, and you have channels on the edge, which counter-propagating channels on the edge. To understand anything regarding these states, you need to make these states interact. Okay, and in a bulk system like this, there is no chance for these states to interact because they are far apart. Because these states cannot talk to this. Okay, this comes back this way. Okay, so the idea here is you make a constriction and bring these edges closer, just like this. So you make a quantum point contact either by etching or by electrostatic gating or a combination of both. And you can bring these edges nearby within a distance where they can interact. Then measure what is the tunneling current between these edges. That is the idea. So if you have abelian system, you will have a certain kind of tunneling distribution, tunneling current. Okay. If you are non-abelian, you have a different kind. And these tunnel conductance are given by this formula, where G is the effective Coulomb interaction parameter and E star is effective charge. And by looking at this, by fitting these tunneling curves using this formula, you can extract information about the statistics, or whether it's abelian, where abelian means you have the wave function under exchange will accumulate a phase factor, and if that phase factor is 2 pi, you get it's a boson. If it's a pi, it's a fermion. Then there's a sign change, and it could be any other arbitrary angle. Then they are called anyons. Okay, and that is not a topic of discussion. Just mentioning just for completeness here. Okay, now if it's non-abelian, this exchange is equivalent to a unitary transformation, and that is where you have the possibility of using the states as to store information and manipulate information. If you have a system of n particle, then there are 2 to the power n different ways you can exchange, and you have 2 to the power n different states to store and manipulate information. That is the concept. And in one of this experiment by Kastner's group in MIT, they have shown that this phi half state could be, they have proposed that by interpreting the results of their experiment, that this phi half state could be abelian. But there are also experiments where the phi half state saying it could be non-abelian also. There are both. Okay. So in one of the experiments they are saying it's abelian, and in one of the experiment using the same sample they also have the possibility saying they are non-abelian. So that is why I'm saying it's not a completely settled field. Okay. So the quantum point contacts, just to summarize, are the poster boy of one-dimensional transport. It's a highly interesting and technologically important and at the same time very intriguing quantum system. One of the simplest systems to make and measure, but with a lot of physics in it. So in the next set of lectures, we will move on to lower dimensional systems. And by this, we will stop the discussion on the one-dimensional transport.